Another way to determine if we have a function is to look at the graph of the function. Remember, if in order to have a function in general, what do we know? The x's can't repeat. Good. So if I'm looking at a graph here, such as something like example 3b, we're just going to ghetto graph this. I'm coming out here to 4, up here to 6, over here to -4, and down here to -6. And I'm just going to connect the dots, la 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 la. So let's assume that this is crossing over here at 4, and likewise up here at 6, -4, and -6. Actually, -6 I did pretty good on. Okay, so here is my graph. If I have this graph, I want to determine whether or not this graph is a function. Now, if I'm going for whether or not the x's repeat, what can you do to determine that? What are you looking at here? Yeah, check this out. What if I put a vertical line through my problem? Remember, the equation of a vertical line is x equals some number. And look what just happened. I've got this point, which is, I don't know, let's just wing it, 2 and some number. And I've got this point down here that's also on my graph here, my original graph, which is, oops, pardon me, that's a -2. Also -2 and some number. So, all of a sudden my x's are repeating. And I have the vertical line, x equals -2, so I know all of my values in that vertical line for x's are -2's. So we have what's called a vertical line test. Your vertical line test determines whether or not you have a function. Cool. If your crosses more than once, then it is not a function. So crosses more than once. Oops, O-N-C-E. Try that again. Not a function. Cool. So check this out. So is this one a function? Nope. We already determined that, so that's awesome. So is this a function, question mark? Nope. But just like any relation, we can always have a domain and a range. Now, what do you think the domain is for this function? Okay, so -4, -3, -2, -1. So you have all those specific points, but what about the points between it? This is a continuous graph. So the graph goes all the way around. It doesn't stop. It is not disjoint at those specific numbers. Let's do a little interval notation. So if I am looking at my values here that I have, we are going to do this arrow. Here I have -4, and then my graph goes all the way through to +4, and the same thing up here. So from -4, every single value between there works until I get to 4. So if I'm looking at this, we put on our meter and we start here. Beep. Ooh, check that out. So my meter tells me I'm going everywhere from -4 up to 4. It's interval notation. Now, why did I put brackets but around the -4 and the 4? Good, because they are included. Those values are part of my graph. The only way it would not be included is if you have a hole in your graph there. Cool, let's check out the range. Again, let's get our meter out and see what we've got going here. So I'm going beep. Ooh, so if I'm looking at my meter, my range is going from what to what? -6 to 6. Now remember, your domain and your range is always small to big. And this is not just saying the points -4 and 4 because I'm looking at a graph. We are using interval notation like what we did with our inequalities. So interval notation, oh my gosh, that's awful. Let's try that again. Yeah, get rid of that. Interval, my handwriting's bad enough whenever I start spelling stuff crazy. Notatio. Notation. Okay, so interval notation from this one to this one and everything in between is what that's saying. Cool, let's look at another one. What if I have this graph, example 3D, where there's my coordinate plane and I have something like that. Cool, now that I got my graph on there, I'm going to go ahead and put my values in. This is going to go down to, oh, I don't know, let's say a -3, 4, 5, that goes to a +5, and that goes to a -1. Okay. That's a -3. Cool. Okay, let's do this right now. We want to lay it out, everything that we know. We want to determine if this is a function, and we're going to state the domain and the range. Okay, first of all, is this a function, and how do you make that determination with a graph? Vertical line test. Okay, so let's do it right now. I've put multiple vertical lines on my graph. Does it ever cross more than one time? No, sweet. So if it's not going to cross more than one time, then yes, this is a function. Cool. Now, let's see if I can go over the top of my graph, make it darker a little bit here so we can actually see it with all those vertical lines on there. So the red is my graph. So let's look at the domain and the range for my graph. We're going to do the same thing again. Now, if I can determine my domain, what values are going to work? What values are going to work for this problem? -1 to 5. Okay, so I'm looking at that. I can see that. But what about all of the values that are over here? So my graph goes up, down, up. And then what does this arrow tell you at the top? What happens? It just keeps going. What does this arrow tell you at the top over here? It just keeps going. Okay. So if the graph just keeps going, then how far to the left am I going to go? Forever. How far to the right am I going to go? Forever. Now, granted, it's going to take a long time to get there just because of the shape of my graph, but whenever you're figuring out domain and range, look at those arrows. Where are the arrows pointing? And that tells you about your domain and range. So my domain is going to go from -infinity to +infinity because you always, always, always want to look at those arrows. Awesome. Now, my range is going to go from what to what? I don't know. Let's get our meter back out again. Is it down here at all? Nope. Beep. Keeps on going because of my arrows. So my graph actually starts right here at -3 and then it goes on to infinity. Cool. So I have a bracket at -3 and then infinity, remember, always has a parenthesis associated with it because you can't actually land on infinity. So this is going from -3 to infinity for this problem. Look at your arrows. Now, my biggest beef when it comes to MyMathLab is the graphs do not have arrows on them. So in that instance, just look at how far your graph goes on the grid that they give you. And then just know it's going to keep going from there. I've even complained to the publisher about it, and it hadn't done any good so far, so it's just a computer glitch on there. But keep that in mind if you're looking at an actual graph. It's where your arrow's going. Watch those arrows so that it helps you with your domain and your range. Cool. Okay, if we recap here just for a minute. We have looked at several different relations in order to determine if they are functions. The first one we looked at were ordered pairs. And regardless of the format, how do we determine if we have a function? What are we looking for? That the x's can't repeat. Good. So we've looked at ordered pair. Oh my. Let me try that again. Yikes. R-E-P-E-A-T. How about that? So the x's can't repeat. If you look at ordered pairs, that's kind of obvious when you're looking at it. Mapping, remember, was the input and the output where the arrows went over. So you knew if it had a double arrow on the input, which is the one on the left, then you know that it was not a function. The t-chart, just like any other t-chart that you're used to doing whenever you're making graphs, the left side are your x values, and those can't repeat. Looking at a graph, you do your vertical line test. And also a graph, so up to this point, the top three, then you use set notation for your domain and your range. You do the squiggly brackets and you just list what it is you have. For your graph, in addition to the equation, when you state your domain and your range, you're going to use interval notation. So ordered pairs, distinct values, therefore you use set notation. Mapping, distinct values, so you use set notation. T-chart, distinct values, set notation. So that is the key. If you just have specific points that you're looking at, that is when you use set notation. The graph, it was continuous, it all connected, interval notation. The equation we're going to look at, it's going to be the equation of a relation. So that means it's going to be like a graph, everything that counts, and therefore we're going to do interval notation. All right, so let's look at this equation first. So here's example 5a. Y equals x plus 4. Now I understand we have not talked about lines yet, but check that out. What do you notice? What can you recognize there? Y equals mx plus b, right? That's a line. So if I'm looking at a line, what do you know about the graph of a line? Look at the arrows. The arrow goes all the way to the right, it goes all the way to the left, it goes all the way up, and it goes all the way down. Is this ever curve back on itself or work with anything like that? No. And check out the actual equation. Your x value will always have 4 added to it. So whatever you put in for x, there's no way that it can repeat. You're always going to have 4 added to it, and that's going to equal your y. So we want to make the determination of, is this a function? Yes, it is. And then we want to find the domain and the range. So my domain for this function, is there anything that's going to mess with the x at all? Nope, it's just an x. So my domain for this is going to be from negative infinity to positive infinity. What about the range? Again, there's nothing that's going to mess with it at all. So I'm going to go from negative infinity to positive infinity. Cool. Let's do more.